Welcome to today's webinar, Eliminate Background, Enhance Detail, Metro Counting Camera for SAED and 4D STEM. Before we get started, I would like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer your questions for the speaker at the end of the presentation. However, if we don't get to your question, we will follow up later via email. Now I'd like to introduce the speaker for today's webinar. Ben Miller has been working on the development of in-situ techniques since 2010, when he began his master's degree project to illuminate TEM samples with visible light. His PhD, working in the group of Dr. Peter Crozier at Arizona State University, focused on the development of operando ETEM to simultaneously observe catalyst nanostructure and measure catalytic activity inside the TEM. In 2016, he joined Gatan as an in-situ application specialist. In this role, Ben collects imaging, spectroscopic, and 4D STEM data demonstrating the capabilities of Gatan's in-situ products and presents the results around the world. He also provides applications training and support to researchers and helps to specify the capabilities of future in-situ TEM equipment and software. Now over to Ben.
Yeah, thanks, Jonathan. So I'm excited to present today on how we can use the Metro counting cameras for both selected area electron diffraction, and I'll talk a little bit about 4D STEM. And the Metro camera, like all of Gatan's counting cameras, really helps us to eliminate background intensity and then to enhance the detail. And I'll talk more about what I mean by that as I go through these slides today. Most of the data that I'll show today, I collected myself with the Metro camera and the Metro 300 camera. A few of the data sets were collected by other researchers. So the Metro camera series are cutting-edge counting cameras that can be used for really groundbreaking low-dose diffraction and 4D STEM studies. There are two cameras. The original Metro camera operates from 60 to about 200 kV. While the Metro 300 camera goes from 80 kV up to 300 kV. So the sensors are optimized for different kV ranges, but otherwise the cameras are identical. There are two sections in my presentation, two main divisions that we'll look at. The first, I'll talk about how we can capture high fidelity diffraction patterns, and specifically at lower dose rates on the camera, but also on the sample. And then I'll talk about how the Metro cameras really simplify some advanced diffraction workflows, whether that's 4D STEM or continuously acquiring in-situ data, diffraction videos, or even just being able to look at a diffraction pattern without extensive setup. Before I get to those two sections, I want to present some data that maybe some of you have seen before. This has been in some other presentations for Metro for a while now. And this pattern that you're seeing is actually a one view diffraction pattern. So one view is a good camera, right? Scintillator based camera. And it can detect many faint diffraction spots. This pattern was captured with a very low dose rate from a zeolite sample. And so we can see some very faint spots in this pattern, but there are also some spots here that are not very well defined. It's difficult to say with certainty whether these are real diffraction spots or they're just part of the noise. And certainly to determine where these spots are located, is quite difficult. But if we just switch the camera, do nothing on the microscope, I removed the one view camera, inserted the metro camera, and take another diffraction pattern, we can see that the metro provides much sharper details and also much less background noise. And so, of course, this would enable you to do better characterization of this zeolite material. And specifically, if we look at these three spots in the center of this profile that I've selected here, we can see that they're clearly resolved, and we can detect them very easily above the noise here. And as I'll talk about later, most of this noise is actually from the sample. This is mostly diffuse scatter from the sample itself. And there is almost no background noise from the camera. But the metro, because we have such low noise, and because the images are so sharp, we can very clearly resolve even these very faint peaks in the diffraction pattern from this zeolite sample. So in this first section, I want to talk more about how the metro can do this, how we can capture high fidelity diffraction patterns, and some of the ways that we can think about the performance of the camera. So I'll talk about how we can detect the smallest signals because of the low background and how counting contributes to that. I'll talk about how this really allows us to look at very delicate samples with a very low dose rate. And how we can very precisely locate these diffraction spots because they're so sharp. And then I'll talk a bit about the dynamic range that would enable you to do quantitative diffraction. So the metro camera is what we would call a direct detection camera, but direct detection alone doesn't eliminate all noise sources. So there are noise sources and blurring effects that you would get from a scintillator-based camera, any scintillator-based camera, no matter how high quality, that would be eliminated by using direct detection. But even when you eliminate those, there are still some noise sources that are present even for direct detection cameras. And so I've listed two of those here, the Landau noise. So this is when, ideally, each electron should contribute the same signal to your image. One electron should give you 1 electron worth of signal in your final image. But in reality, electrons deposit different amounts of energy in the sensor. So 1 electron may deposit a lot of energy, as you see some of these larger, more intense spots in this image, and some electrons might deposit less energy. And there's a statistical distribution that characterizes this Landau noise, and it has a very long tail. And so the ultimate effect of this is that for very low intensities, low dose rates, you get a lot of uncertainty in the amount of electrons that have contributed to any given signal. There's another type of noise, readout noise, that also is still a problem for direct detection cameras. Ideally, you would want pixels that don't have any electrons hitting them to have an intensity of 0. But reading the signal in any real sensor does generate a small amount of noise. And so you can see that in this image that I'm showing here. The background is not exactly zero. It's small. It's actually very small compared to the signal from electrons here, but it's not zero. And if you were only reading out one time, this would not be a problem. But as you start to read out hundreds or thousands of times, you start to accumulate more and more of this readout noise. And this becomes a problem, even for direct detection cameras. Now, there's a solution to this. We need to do electron counting. We need to count these electrons one by one. And so I'll show what I mean by that and how that's done in the next slides. So as each electron hits the detector, it creates a cloud of charge, right? And this varies from one electron to the next, but in detectors like the Metro or the K3 that have very small pixels, this will span several pixels. And this charge is then collected in each pixel to give you an image. And if you do that, you would get something like this image I'm showing here. Now, this would be okay, right? You would get an acceptable quality image, I suppose, with this, and you might call this a linear image or linear accumulation. But if we apply a counting algorithm, like we do at Gatan, this reduces the multi-pixel charge cloud to a single electron event in one pixel. And this results in much sharper images. And for all of Gatan's counting cameras, K2, K3, the Metro cameras, Alpine as well, these all apply this counting algorithm in real time as the data is being collected. So thousands of times per second, this algorithm is applied to these very large images, and we're able to count the electrons in real time as the camera is acquiring. So what this does to an image like the one that I was showing before is it transforms it from something with a lot of variation from one pixel to the next and a lot of background to something with just ones and zeros. And so you can see this again here. We've eliminated this variable signal from the Landau noise. So now every electron produces a single electron event. And we've eliminated the readout noise. So the vast majority of the readout noise is completely eliminated. And all of these pixels that we see here that are black are exactly zero. And so this means they contribute exactly zero noise to your final images or your final diffraction patterns. So what does this look like in principle in practice for a diffraction pattern? Here I'm showing very long exposure dark images. So these have no beam, no real signal. And so ideally, you would want these to be exactly zero, completely black and every pixel exactly zero. On the left, what we see is a dark image from a scintillator camera, like the OneView. And the distribution of noise looks very good. This is on a log scale, so this is a Gaussian distribution of the noise. The dark image looks very flat. There's no discernible long-range pattern here. But there is still variation from one group of pixels to another. And we see this sort of speckle pattern that would interfere if you were trying to look at very, very faint signals in your diffraction pattern. Now, on the right-hand side, we have a dark image from the Metro camera, actually the Metro 300 camera here. And we see that the vast majority of pixels are black. And this means that they are exactly zero. They're adding exactly zero noise to the final pattern. And these dark images were 10 seconds long. So this is quite a long time of adding together any residual readout noise that we might have, or any spurious, perhaps X-rays or other events. And so we see here that in this 10-second image, we are getting only a few false electrons. And if you go back and calculate this, there's actually 3.15 billion reads that are happening here. And only about 1,000 false positives per second. So this is 1 in 3 million times that the detector and the algorithm gets this wrong. So the other 2,999,999 times, it gets it right, that there's no electron in the pixel. So it's an extremely precise and accurate algorithm that is excluding almost all of the readout noise from the sensor and giving you a very dark image. And this is, again, critical for capturing weak diffraction spots. So this enables us to work with very delicate samples, right? We can use a low dose rate on the sample, and we can detect very small diffraction peaks with the camera. This example here is a covalent organic framework, a COF, or also you could call this a 2D polymer that's highly sensitive to the electron beam. And so a very low dose rate was used here. But Metro still detects the weak, high resolution diffraction spots here because we have such a low background. So in many cases, even on this log scale plot, we still don't see the background from the camera. It's below this 0.2 electrons per pixel at the bottom of this plot here. If we had this on a linear scale, we would not even see the diffraction spots here because they're so small compared to the diffraction spots toward the center of the pattern, where we have thousands of electrons per pixel. Another feature of the camera, because we're doing counting, because again, we take a distribution of charge that's deposited by each electron and convert that to a single pixel with a single electron event. This means that the images can be very sharp. We have almost no blurring, unlike scintillator-based cameras, like the OneView or even our latest ClearView camera that have unavoidable blurring from the scintillator, fiber optics, etc. Counting means we have virtually no blurring. And so we can locate spots in the pattern with very high precision. If we look at this particular spot in this graphene diffraction pattern, we can see that the highest intensity is really only in one single pixel here. And if you measure this and determine how large is this pixel in reciprocal space, how precisely can we locate this spot? It's within 0.005 angstroms. It's very, we can locate these spots very precisely because the patterns are so sharp. And in many cases, you can actually see some details of the sample itself, maybe of the geometry of the sample from these diffraction spots that will actually have some structure within them. This one is mostly just a single pixel, but it with the very sharp patterns that are produced by the camera, you can start to see interesting detail within single diffraction spots. The next thing that I want to talk about was dynamic range. So we've already seen this to some extent with the previous diffraction patterns, but spots with intensities spanning 3 orders of magnitude can be easily detected and precisely located with this camera. This diffraction pattern here is a 5-second exposure. So quite a reasonable exposure time, I would say, for diffraction. And while the center spot here is too intense for every electron to be counted, other intense spots can be quantified. So this profile here is not going through the center, but it is going through some very intense diffraction spots that we can see in the graph here. And if I start to zoom in on this same profile, we see that there are actually a lot of diffraction spots out at higher resolution. That if you're looking just on a linear scale plot, you can't even see them hardly. But here we can see that we detect these very faint spots quite clearly above the noise. Again, because there's so little background from the camera, and because the images are so sharp. So you can very easily detect these sharp diffraction spots. And maybe I should also point out here that toward the center of this pattern, you see that the background intensity is much larger, but this is background intensity from the sample. This is real data, real information from the sample. Now, it's probably not the information that most people want. It's perhaps inelastically scattered electrons or just diffuse scatter. But that's real signal. Even out here, most of this background around this very small peak is actually real signal from the sample itself. But Metro enables us really to handle both these very low intensity spots and also the high intensity spots without damaging the camera. And I'll talk more about that a bit later. So this dynamic range is also really helpful for quantitative seabed diffraction, convergent beam electron diffraction data. We can also get really nice high fidelity patterns in seabed mode. And so this enables really high resolution images and diffraction patterns that are essential for detailed structural analysis. So here we can see that we can image very faint Holtz lines, Kikuchi bands in this pattern. And it might look like this pattern has a completely saturated center spot, but actually that's not the case. That's just due to the display limits, the contrast limits here. If I change the exact same image to different contrast limits, we can see that the center spot is not saturated, and we can clearly resolve a lot of detail within that center spot, like these Holtz deficiency lines that I'm pointing out here. But of course, at the same time, from the exact same diffraction pattern, we can clearly resolve the excess Holtz lines that are corresponding. And so with this large dynamic range in these diffraction patterns and the high pixel resolution, this 2K by 2K pixel resolution that we have here, we can see a lot of detail in convergent beam electron diffraction patterns, and perhaps do some really nice structural analysis, probably with the sample tilted a bit better than I've done here. I'm certainly not an expert on seabed, and I personally don't know what to do with a pattern like this. But for those of you out there who do convergent beam electron diffraction, I hope that you can see the potential here for capturing and getting some really nice information from your sample. So the next big section of this talk, I want to talk about how the Metro camera simplifies advanced diffraction workflows, whether that's just being able to find the pattern center, which sometimes is non-trivial, as I'll talk about in a moment, or capturing high quality 4D STEM or in situ diffraction videos. The Metro camera and the software that comes with it can really enable you to simplify these and rapidly collect some really nice data. So traditional cameras often require a beam stop for capturing diffraction. And this makes accurately identifying the pattern center rather challenging, right? So if I zoom in on this pattern and I want you to point out which pixel has the exact center of this diffraction pattern, you could probably get close just by eyeballing this, or perhaps you could have some very sophisticated algorithm that would somehow determine the pattern center with accuracy. But it's non-trivial, right? To determine exactly where is the pattern center, what pixel is the center of this diffraction pattern. But with modern Gatan cameras like the Metro, or even the Clearview or Rio or Stella or K3, all of these modern Gatan cameras make it easy to precisely and accurately identify the pattern center because a beam stop is not required. And so we do need to be careful about the intensity that's hitting the camera, right? You need to set up your diffraction well to do this on the Metro. But we can do that pretty easily. And once you have a pattern with no beam stop and you can see the center of the pattern, this enables you to more accurately measure all of the diffraction spots, right? Because you're always going to be measuring them with respect to the center. The Metro camera is also engineered for long-term durability. So I don't know if any of you watching this already have been wondering, you know, have they damaged the camera? Is this all this diffraction decreasing the lifetime of the detector? And I would say emphatically the answer is no. All of this diffraction data that I've showed has not damaged the Metro camera. And if I go back and play this video again, I want you to watch. I start the video in diffraction mode with the center spot right on the camera, and then I switch to imaging and put the beam right in the center. If the camera was being damaged, we would see a little burn spot in this image. And especially, you know, if we had a flat field image and no sample, you would be able to see that very clearly if there was any damage to the sensor, even very minor damage. But we're not seeing any of that here, right? The diffraction spot is not burning the sensor at all. And in fact, this is only the first part of a much longer video where for 2 minutes, I recorded diffraction while some tin nanoparticles melted and recrystallized. And I was able to do an entire real in situ experiment on this sample without worrying that I was damaging the camera. Metro also can be used for 4D STEM. This requires the optional STEMX product from Gatan as well. STEMX is the tool that synchronizes the camera with the DigiScan to sync the scanning with the acquisition. But with STEMX, Metro can be used to collect some really nice high quality 4D STEM. And the data that you're seeing here on this slide is not necessarily from the Metro camera, but any of these data sets, we could collect similar data with the Metro for sure. And we can use tools in DigitalMicrograph to do a variety of different processing and analysis techniques, including most recently, we've added a new STEMX OIM package to our software offerings. And so now this enables orientation mapping, which I'll show here on the next slide. So this is a direct comparison between an orientation map collected with the OneView camera and with the Metro 300 camera. These were, again, both on the same microscope here at Georgia Tech in this example. And so they were able to capture one data set with OneView, one data set with the Metro 300 camera. And they can see that the diffraction patterns are much higher quality with the Metro camera. There's virtually no camera noise, no background from the camera itself. And so this gives you higher signal to noise diffraction patterns. And of course, this results in better analysis, right? So you get improved orientation maps with higher confidence. And so in these images that I'm showing, all of the white regions are areas that just couldn't be indexed based on the data that they had. Despite some really nice processing techniques, they just couldn't be indexed. Where with the Metro, there was much less of these areas that could not be indexed. We have much better confidence in the pattern indexing here. Metro also enables us to capture in situ or continuous acquisitions over time. And I want to talk about two ways that we can use this. The first is to just monitor damage of very beam sensitive samples. So again, as we talked about at the beginning, the Metro camera, because we can use such a low dose rate and detect such very faint diffraction spots, we can use this to acquire diffraction from very beam sensitive samples. So this here is a MOF sample, and we were able to capture this data at 0.09 electrons per angstrom squared per second, with really minimal damage to the sample in this first 10 seconds. So in a 10-second diffraction pattern here, we can see nearly pristine structure of this MOF sample. But if we continue to image this, continue to expose this MOF sample to the beam for a longer period of time, here about a minute and a half, we can see that at this same very low dose rate, the sample is ultimately destroyed. In about a minute, I would say, most of the structure is gone. And so being able to capture in situ diffraction videos like this enable us to precisely monitor this damage over time and even quantify how rapidly is my sample damaging, how long does it take for it to get down to a certain resolution, for example. And so it makes it very easy to do this with in situ cameras like the Metro. And unlike the clear view or the one view, the Metro camera is always in situ capable. So there's no PC upgrade required, there's no software upgrade required. Metro by default is in situ capable and can collect nice videos like this in imaging mode, but also in diffraction for monitoring samples in this way. We could also use this in situ acquisition to capture real in situ experiments. Here, this data set I'll play in a minute. We're going above and below a transition temperature here in this vanadium oxide sample. And we'll see the changes in the diffraction pattern quite somewhat subtle, but also very easy to see with the powerful processing techniques that I'll show. But all Gatan cameras, including Metro, have these powerful free tools in DigitalMicrograph. Data is synchronized, it's all linked together, as I'll show in a minute in this video, and the data can be processed live during playback. And then ultimately, we can process and export the data in a single step to a variety of formats, whether that's an MP4 video for a PowerPoint, or a series of TIFF files for further analysis, or a new in situ data set that would be synchronized, as I'll show here. So at the top left in this video, we see the original data set, the original in situ diffraction video. But on the bottom left here, I have a moving average that I've calculated with the free tools here in DigitalMicrograph. And so I've just saved this process data as a new in situ data set. And now as I play these back, they're automatically synced together. I also have a profile tool on these diffraction patterns that is being applied live. And so these profiles in the bottom right corner are being calculated live and they're synced together. So if I move the profile on one data set, it will also move the profile on the other data set. And so we can see both the original raw data in red here, and the processed, moving average data in blue. And we can see as the temperature oscillates above and below this transition temperature, we can see the peaks here appear and disappear as the structure changes from monoclinic to something else, I forget. But in this vanadium oxide sample, it goes from an insulator to a conductor as you oscillate the temperature here. So we can do real in situ experiments with the Metro camera. So just to summarize again, what I talked about here today, we were able to capture high fidelity diffraction patterns, even at very low doses. And the Metro also simplifies some advanced diffraction workflows like in situ acquisition or 40 STEM to enhance your efficiency and the precision with which you can measure peaks, for example, with the center visible. The one last thing that I want to do before we go to answering questions is I just want to point out, I talked in this presentation all about diffraction, right? So all of the Metro data that I showed were diffraction patterns or 40 STEM. But while the diffraction performance is impressive, the capabilities of Metro for low-dose TM imaging and for in-situ TM imaging are also best in class. And I could go on and on. I would love to spend another hour talking about all of this capability as well. But we already have some really nice presentations on these topics out there. So today I just wanted to focus on diffraction. If you have any questions for me, please, as Jonathan said at the beginning, you can submit those through the questions pane. And if we don't get to your question, I will send you an answer via email and follow up there. But happy to answer a few questions live in real time here.
Thank you very much, Ben. Nice presentation. There are a few questions actually, so maybe I will just dive in. One of the things that you mentioned a couple times was that we need to be careful how we set up the camera and the microscope when we collect diffraction images on Metro. Can you elaborate on that, please?
Yeah, so essentially what I do, my workflow for setting up diffraction on the Metro or the K3 or Alpine cameras, any of Gatan's direct detection cameras, is to first put in the selected area aperture on the microscope, and then change the magnification so that that selected area aperture is entirely within the field of view of the camera, and then adjust the intensity of the beam until I have a good number of electrons hitting the camera. So in diffraction mode, when you have the microscope in diffraction mode, it's really hard to measure how many electrons are hitting the detector. But in imaging mode, it's very easy to count every electron one by one and determine how many electrons am I going to be putting into my pattern. And if I just assume that all of those electrons are going to go into the center spot, then I can decrease my intensity so that even if all those electrons went into just a few pixels, I would still be okay, and I wouldn't be damaging my camera. And so actually we have an entire web page about this. So if you're interested and you want to learn more about how to set up diffraction on any of Gatan's counting cameras, you can go to this web page. I don't know, Anna, do you see the web page that I'm showing?
Yes.
Great.
Yes.
So you can read through this, and you can even just quickly scroll through and read the blue parts. So we've tried to make it a bit easier to digest. And you can see even some of the data that I showed today is there as well.
Thank you, Ben. There's another question asking, can you briefly compare Metro with the K3 camera? Everybody knows the K3. How does Metro compare?
Yeah, so with respect to performance of the camera, I would say they are very similar. So the algorithms, the technology behind these two cameras are nearly identical. And so whatever performance that you would expect from the K3, you can get with Metro as well. But the Metro camera is, I like to use the word accessible. The Metro camera is more accessible than K3. So what I mean by that is, number one, the software is much simpler. K3 is very powerful and very flexible, but that also means it's a bit complicated. And Metro is designed to be very simple, very accessible to new users, to students. The user interface for Metro looks identical to the OneView, for example. So anyone who's ever used a OneView camera will be quite familiar with the software interface. And then the price as well is more accessible than K3, for a lot of labs.
Thanks, Ben. Can we do energy filtered diffraction on the Metro?
No. So the Metro camera is only can only be placed above the GIF. We don't put the camera at the end of the GIF to be able to do energy filtering. If you wanted to do energy filtered diffraction, you would need to get the K3 at the end of the GIF or Stella. But yeah, K3 at the end of the GIF would give you very similar performance to what I've been showing today, but with energy filtering, which is even better.
Yes. Okay, I think we will keep the rest of the questions to be answered offline. I would like to thank you, Ben, for presenting, and thank everyone for joining us today for this webinar. Have a great day.
Yep, thank you.